We reminded ourselves last lesson about potential difference and its connection to energy, and the electric current and its connection to charge. And we're going to pick that up today, and we're going to use those ideas to gain an understanding and some ability to predict how much energy is delivered by our electrical appliances in our homes. So the title for today's lesson is Electrical Power. This PowerPoint is available on Google Classroom, so you can either make notes as you go along, or you can make them at the end, or a little bit of both. Okay, we need to start with a definition of an everyday word, which is power. So in physics, what the word power means is how quickly energy is transferred by a device or a process. So it has a real meaning, a definition. So let's look at some examples. So let's think about a kettle. Let's pretend that the kettle is heating up some water and is doing so by taking electrical energy from the electric current and passing it to the water as heat energy. So here are some numbers. We've got 8,000 joules of energy that have been transferred, and that took 8 seconds for the kettle to do it. So we could refer to the power of the kettle as 8,000 joules per 8 seconds. And we've played this game before yesterday with current and potential difference, and now we're doing it again with this other concept, electrical power. Just like we did with potential difference and with current, it's much more normal to refer to these things as per one rather than per 8 or per random number. So rather than saying 8,000 joules per 8 seconds, it's much more normal to say 1,000 joules per 1 second per second. So if you're making notes, the thing that you need to write down is that power is how quickly energy is transferred. Power is how quickly energy is transferred. Okay. So units, well, we've just agreed that we will use the joule per second as the unit of power, as opposed to the joule per 8 seconds. We're going to use the joule per second. And these slides are just like the ones for potential difference and current. So you've seen this one before. What we're going to do is take the perfectly fine, nothing wrong with it, joule per second, and we're going to name it after a dead person. So in this case, it's James Watt from Scotland, 1819. So again, 201 years old, 202 years old that this definition is. It would be so much simpler to just refer to the joule per second, and then we would all remember what power is and what units it is. You have to memorize that the unit of power is the watt, W-A-T-T. Symbol is a capital W, and it's 1 joule per second. So in terms of your notes, you need to write down, yeah, the watt. You need to write down that the unit of power is the watt, W-A-T-T. 1 watt is 1 joule per second. Okay, so similar to, again, what we did for potential difference and current, how did we turn 8,000 per 8 seconds into 1,000 per 1 second? Oops, typo on the slide there. That should be 1,000, not 10. So we just need an eighth of the 8 seconds worth of energy. We're going to assume that the 8,000 joules were delivered evenly across the 8 seconds. So if there were 8,000 joules in 8 seconds, then there was an eighth of 8,000 joules in each of those 8 seconds. So we're just going to divide by 8. So if we write that as a formula, that's our way of calculating the power of a device. So power is energy transferred divided by time. You need to write that down and put it in a box and make it look important. Right. When we're done with this electrical topic, we're going to move on to a topic all about motion, force, and energy. And you've already studied energy a little bit in year 9. We're going to come back and remind you about it in the next topic. You might remember from year 9, you might not. If you don't worry, we're going to study it again in a few weeks' time. A kind of historical term for the amount of energy that has been transferred is historically it's often referred to as the work done by the machine or the process or the force or whatever it is that's transferring the energy. It doesn't make very much sense these days, the work done. It just sounds like a really odd term, and it is an odd term. But just be aware that sometimes you will see this formula printed in revision guides and textbooks, in YouTube revision videos, occasionally on exam papers. You will sometimes see this formula printed with the phrase energy transferred replaced by the phrase work done. The two things mean exactly the same thing. It's just a historical term that just won't go away. So just be aware of the fact that the phrase energy transferred and the phrase work done are used interchangeably. Energy transferred is kind of the more modern version. Work done is just a historical term that we're stuck with. So you might want to just make a little note, just maybe draw an arrow to where you've written energy transferred and just scribble down that sometimes this is written as work done. Like I say, if that is seeming odd to you or not ringing any bells from year 9, we will come back and revisit this when we're doing the motion, force, and energy topic, which is coming up next. Okay, as with the other two formulae that we have already looked at this week, it is often much more useful to have a rearranged version of this equation because often we know what the power is. And the reason that we often know what the power is because certainly in the UK by law, all electrical appliances have to have the power that they consume printed on them somewhere. So if you go find your, I don't know, your kettle or your hairdryer or any device in your house that you can get to the back of or the bottom of, please don't start turning your TV over or taking it off the wall or anything like that. But if you can find a device in your house, even your mobile phone charger, probably, if you go find it, somewhere on it, it will be printed a number with a W after it. And that is the power that the device consumes. And so it's often a number that we know. And so we can use this rearranged version of the formula to read the power from the appliance. It's like I say, it's printed on the appliance from the manufacturer. They know how much power it uses, so they have printed that on. And then obviously we can tell the time using a watch or a stopwatch. So as we discussed last time, measuring energy transferred is actually quite difficult to do. So we can deduce it using this formula from the power of a device and the time that the device is on for. So here's an example. Say you spend 8 minutes drying your hair with a hairdryer, and the hairdryer has printed on it 1500 watts, 1500 W. And so how much energy did it transfer while it was drying your hair? Well, it transferred the 1500 watts multiplied by the time in seconds. So just make sure that you don't forget to convert the minutes into seconds by multiplying up by 60. And here's where you note that the joule is a pitifully small unit of energy. It's 720,000 joules is transferred to your hair every time you dry it, which is ridiculous, isn't it? 720,000 joules. And it's a similar amount of joules for making a cup of tea. Hugely more than that for having a shower in an electric shower. So it really brings home the fact that the joule is a useful unit for using in little science experiments in a science laboratory. But when you actually bring it out into people's homes and start using the joule as a unit for simple things like a hairdryer for 8 minutes, it just shows up that the joule is ridiculously small. So it's quite normal to switch to kilojoules. So the K just means add 3 zeros, times by 1,000. And just like kilograms and kilometers, this is a kilojoule. So I'm just going to give you a second to make sure that you have finished copying down the rearranged formula. And I would suggest you scribble down the example as well, because you're going to be doing some questions like it in a minute. So I'm just going to give you a minute to do that. Okay, so another 20 seconds on that, and then we'll push forward. So everything, slide for slide, that we have done so far today has just been exactly the same as what we did for potential difference and for current. This is obviously new, though, because you haven't done this before, but we haven't gone any further. We've just provided an equation and rearranged it, given an example. What we can do now, though, is start to glue the formulae together. So if we just oh, sorry, I forgot I got this slide coming up. So just to put the word power in context, I don't want you to get the impression from the everyday use of the word power that it's about the end goal. So you might think that, you know, if you've got if you're a powerful person in everyday life, that kind of implies that you're capable of doing something that less powerful people can't. So, for instance, the prime minister of any country is a powerful person. He has or she has a lot of power. And the prime minister is therefore able to wield that power and do things that other people can't because they're not the prime minister. The word in everyday life isn't quite the same as the word in physics. So a powerful device can't do anything that a less powerful device can't. All devices can achieve the same output, the same end result. In physics, it's about speed. A powerful device or a powerful process just gets there first. It's quicker. Remember, it's about speed. Joules per second, not joules. It's not about how much is accomplished. It's about how quickly it is accomplished. So in physics, a powerful device isn't one that can do stuff. It's a device that can do stuff quickly. So for instance, if you've got two kettles, the higher power kettle will boil the water more quickly, but they will both boil the water eventually. A high power hairdryer will dry your hair quicker, but they'll both dry your hair. A higher power crane motor can lift things, and so can a lower power crane. They'll both lift the same weight. It's just that the higher power crane motor will lift the weight more quickly. A higher power bulb compared to a lower power bulb, they both light up the room. It's just that the higher power bulb throws light out into the room at a faster rate. Which means if you were looking at it, more light will be landing in your eye every second, and so you'll feel that the room is brighter. But both bulbs are still lighting up the room. Heaters, lower power versus higher power. The higher power heater will just heat the room quicker, but they'll both heat the room. Speakers, higher power speakers versus lower power speakers. The higher power speaker will emit more sound energy each second, but they both make the same sound. It's just that your ears will interpret one as being louder than the other. So I don't want you to think that power refers to being able to accomplish something versus not being able to accomplish. It's all about speed. Powerful devices do exactly the same as low power devices. They just do it more quickly. Okay, this is where we're going to glue the formulae together. So the definition of power is generally true that it's the energy transferred per second. And that's true of everything. That's true of you. That's true of someone banging a drum, making a sound, anything like that. But when you're talking about electrical devices, we've already got some formula involving energy. So we know that the energy transferred is related to the potential difference. And we also know that the time is related to the current. Now, that blue words and that green words, those are the two components of power, the energy transferred per time. What we don't really want to be bogged down with when we're talking about power is the charge, which interestingly appears in both of these formulae. Now, what we're going to do then is a little bit of maths. We're just going to multiply the two numbers together. So we're going to times the current by the potential difference. But the current is just the charge divided by the time. And the potential difference is just the energy divided by the charge. So we can replace current by charge over time, and we can replace PD by energy transferred over charge, and then we can do that middle sum, charge over time times energy over charge. And if this was a maths lesson and this was algebra and you had something like C over T times E over C, I hope that you would be happy cancelling out the charge. One's on the top, one's on the bottom, and you know that mathematically you're allowed to cancel those things out. You've got, say, a 3 on the top and a 3 on the bottom. 3 over 3 is just 1. They cancel each other out. Which leaves us with our formula that we're now familiar with, the energy transferred divided by the time, which is the definition of power. So, yes, power's lovely to have a really formal definition, energy transferred divided by time, but actually, we don't really have an energy transferred measuring device, remember. We much prefer to base our definitions or base our formulae in quantities that we can actually measure easily. And so we end up with the formula that yes, power equals energy transferred divided by time, but actually that's exactly the same as current times potential difference for electrical devices. So as we discussed last time, ammeters are, really cheap, easy to use devices that we've got loads of lying around the lab. Voltmeters the same, which means it's really easy to measure current and potential difference, get out our calculator, multiply them together and work out the power. So if you didn't know what the power of your kettle was, you just need to plug it in and attach a current, attach an ammeter and a voltmeter to the circuit, and whatever it says on the two screens, multiply them together, and that will give you the power of the device. And that's what the manufacturer will have done when they made the thing. They'll have plugged it in, attached an ammeter and a voltmeter, seen what it comes out as, and then whatever that is, they'll have printed that on the box so that they can tell their customers what power the device is. And customers might want to know that for a couple of reasons. So if you are going out to buy a kettle or a toaster or a hairdryer or a power shower or whatever, you might think to yourself, you know what, I don't want to be waiting for my toast. I don't want to be waiting to dry my hair. I don't want to be waiting to boil my kettle. I don't want to have water that's only lukewarm, because before the water gets heated up to the high enough temperature, the water's already passed through the shower and spilt onto my head before the shower had time to heat it up. I want powerful devices. So you might go to the shop and you might think, right, I'm going to buy myself a kettle. And there on the shelf is a kettle, and on the box it says 1500 watts. But then right next to it on the shelf is a kettle that says 2500 watts. And you'll think to yourself, you know what? Both of those kettles will make me a cup of tea, but the 2500 one will do it quicker and I won't have to stay around waiting for the kettle to boil. Or when you're fitting a shower in your home, you can buy a 9000 watt shower or a 10,000 watt shower. Both of them will give you a shower in warm water, but the 10,000 one will probably have chance to heat the water up to a higher temperature in the really short time that the water is passing through the box. It'll get it up to a higher temperature because it's faster at heating the water. And the water's only passing through the shower for a second or so on its way from the pipe to your head. So that second is all the shower's got to heat the water up. A higher power shower will get it to a higher temperature in that 1 second. So we like the fact that there is an electrical version of the power formula, because it is based upon electrical quantities that are easy to measure. We usually do know what the current and the potential difference is, but we often don't know what the energy transferred is. So we like the electrical version of the formula. So could you please make sure, if you haven't done so already while I've been talking, that you have put the electrical version of the power formula down, current times PD, and stick a box around it and make it look important. And then why stop there? We get very excited about formulae in physics, and you'll notice that there is another formula that's got current and potential difference in it, and that's the one that involves resistance. So there's our V equals IR equation, PD equals current times resistance. And again, very often we will know what the resistance of an object is. So there's another formula where all we've done is look at the power equals current times PD formula, and then we've just swapped out the PD. You can see it's PD is current times resistance. So we can write the power formula as power equals current times resistance instead of PD. Tom, you need to write down all of this slide. So there's another version of the power formulae, current squared times resistance. Or maybe it's the PD we want to keep, and the current we can get rid of. So current is just PD over resistance. So now we've got power equals PD over resistance times PD, which gives us our fourth formula for power. Spoilt for choice is what I will say. It is very, very, very common that either we want to know what the power is, so we're trying to calculate it, or we already know what the power is and we're trying to find out what one of the other things is. And so you need to memorize something like, I don't know, 30 or so formulae for this course. You'll meet 30 or so formulae for this course. 4 of them, no less than 4 of them, are definitions of power or formulae that tell you what the power is. I can't emphasize enough how important the formulae on this screen are in terms of your ability to calculate electrical things. You can see what's coming up. We need to do some practice involving these formulae. However, the one that I just want to point at, I just want to show you or just talk to you about this one first of all, this top right one. We spoke when we were doing fuses about knowing what the current is that works through a device. Well, the device has the power printed on the device, and the mains electricity is always 230. So all you need to do, if you want to know what the normal working current of a device is you just go look on the box, look on the packaging, or look on the back of the TV or the bottom of the kettle or something like that. Find out what the power is. It's the number with the W on it, the number of watts. Find the power, and then all you need to do is divide by 230, because the mains electricity is always 230. And that will tell you the normal current that's running through a device. Okay, there is some practice of doing exactly that on this page. So all of those formulae that I have just gone through, they're all on this double page spread in the textbook. And as is traditional, there at the end are some questions. And some of those questions involve, which fuse should I put in a plug? And that's what I was just talking about, that if you just divide the power by 230, it will give you the normal working current. So we have got half an hour, well, 25 minutes of this lesson left. If I went a little bit too fast and you didn't quite get time to write down all the formulae, then you've got a chance to pull up the PowerPoint yourself from the Google Classroom post and finish off your notes. But then also on Google Classroom is the Chapter 5 PDF. Again, just to be clear, please do not start at page 1. You need to zip through that PDF until you find 5.3, which is the power and potential difference one. And then when you find 5.3, do those 4 questions, please. Then skip to the end of the PDF and mark them to check that you got them correct.